Hi, I'm Keizo Matsubara, and I will give a talk today, which is part of a series of talks in the project Space and Time After Quantum Gravity. There are two different things I would like to talk about today. The first one is, what is philosophy of physics, and why is it relevant for physics? Why is this something that we should care about? The other thing is the problem of quantum gravity, which is a problem within physics. And I would also like to address why philosophy of physics can be important and interesting to help solving the problem of quantum gravity. So some might find it quite weird. Why should philosophy talk about physics? What can philosophers contribute to this? Couldn't just the physicists themselves deal with the problem of quantum gravity? Well, sure, to a large extent they could. But I think that philosophy can actually help and contribute to the development of physics in an interesting way. And that is part of what I will discuss today. However, before doing that, I would like to briefly explain what the problem of quantum gravity is, and thus also give a short background in physics. So, many of you might know that in the 20th century there was a large and important change in how we thought about physics. Before that, the classical physics, grounded in Newton's mechanics, had been extremely successful. There had been other developments like Maxwell's classical electrodynamics and many other things. And all of these had been very, very successful. And there were an abundance of empirical and experimental support for these theories. So there were very good reasons to take them seriously. However, there were some minor problems and mysteries that couldn't really be solved within the framework of those theories. And that led to radical changes in the theories of physics. The first thing I would like to mention is the relativity theories, because there are actually two different theories of relativity. The special theory on the one hand and the general theory on the other hand. Both of these theories are intimately connected to Albert Einstein, even though, of course, there were some other scientists that were important in developing the theories, but Albert Einstein is obviously the most important name associated with these theories. And there are a lot of weird, strange consequences of these theories that radically changed our views about space and time. And furthermore, gravity was now understood in terms of curvature of space-time, something that is quite counterintuitive and weird compared to a more common understanding of the world. Another thing that was perhaps even more radical and even more of a change from the earlier view was quantum physics. And with quantum physics, I include all different kinds of theories that are quantum theories, including quantum mechanics, quantum field theories, and so forth, that were developed during the 20th century. And many people know about this weird thing that particles can behave as waves, and we cannot really predict what will happen, only give probabilities and all these kind of things. And there is still no clear consensus about how to really understand what quantum physics tells us about the world. But this is something that is still under discussion. On the other hand, it's very important to know that even though both relativity theory and quantum physics seems to be very, very strange and counterintuitive theories going against common sense, they are very well established. This is not some kind of mumbo jumbo that we can discard or not take seriously. They are extremely well tested experimentally, even though it might be difficult to understand what all of this really means. And furthermore, there are so many different technological applications of this. So this is a kind of part of our modern scientific and technological understanding of the world. Just mentioning a few examples: lasers, nuclear energy, semiconductor technology. And the last one, semiconductor technology, is extremely important in all modern computers. And I'm not talking about quantum computers here. I'm talking about the ordinary computers that we already have. So no one can kind of discuss or put into question that these theories have been successful and been useful for developing these kind of things, and there must be something in these theories when they've been this successful. When it came to Einstein's general theory of relativity, talking about curved space-time and all that kind of weird stuff. For a long time, there was not that much in terms of technological applications that we could use, but that has actually changed now. And one thing that people are using all the time now is the global positioning system, the GPS, that you can access on your phone to figure out where you are. And interestingly, if one tries to use Newton's theories for this, the thing goes completely wrong and it becomes basically useless. You have to use Einstein's general theory of relativity to get everything right for this thing to work. So that's an interesting thing to remember the next time you want to figure out where you are and look at your phone, that you're actually taking advantage of Einstein's general theory of relativity. And that's quite cool. So we have basically seen now that there have been a large change in physics from the classical physics before the early 20th century to what we now have. And of course, the classical physics is often still useful, even though we nowadays think of it as kind of more of an approximate description. But it might very well be the case that we have to make a new change, perhaps as big as the one we did in the early 20th century. Because while the relativity theories and the quantum physics is very well established in itself, we don't know how to fit them together. And there are situations where we actually need to understand both theories at the same time to understand what's going on. I'm talking about cases like black holes and the early stages of the Big Bang and things like that. So in one way or another, the general consensus is that we need to find some kind of quantum theory of gravity, because it's basically gravity that is the thing we don't really understand in the same way as we understand the quantum theories. So the general view is that we need to modify our understanding of gravity in some way to formulate a quantum. And now there are different competing approaches to quantum gravity. And the most famous ones are probably string theory and loop quantum gravity, but there are other approaches as well. It's important to point out that all of these are still work in process. We don't really know which one of these is right. We might have favorites, but at present they are not well established in the same way as the theories I just talked about, the relativity theories and the quantum physics I've talked about before. This is kind of more speculative work that people are kind of trying to find some new progress in physics. Well, to solve the problem of quantum gravity might lead to new conceptual changes, perhaps as big as the ones that happened in the 20th century. On the other hand, we have problems with quantum gravity because it's so difficult to test it experimentally. So how should we test things experimentally? And perhaps we should even reconsider scientific methodology. Some people have actually suggested that. And these kind of conceptual and methodological questions are both philosophical questions. And for that reason, I think that philosophy can help to contribute in that. And I will now briefly talk a little bit about philosophy in general, and more specifically about philosophy of science and philosophy of physics. So some people, especially some prominent scientists, have talked quite negatively about philosophy and said that it's practically useless. And is such an attitude warranted? I would say it isn't. I think science can actually be quite helped by philosophy. And it's important, I think, to remember that science actually grew out of philosophy. What we now think of natural science was actually used to be called natural philosophy. That in itself might not mean that much, but I think it is important to remember. Another issue is that philosophy is a much broader subject, and there are issues in philosophy that we will not at all address here, like questions about ethics or political philosophy and such things. Here the focus would mostly be about philosophy of science, and in particular philosophy of physics. So one might ask, what does a philosopher do? So typically a philosopher thinks about questions that are controversial in one way or another. They tend to look at things that other people take for granted and question and investigate, is this really the right way of thinking? And some might think that the fact that there is no real consensus in philosophy, they're always kind of arguing with each other, and there are these kind of controversies all the time, that is a reason to not take philosophy seriously. But I don't think that is a good reason, because the controversial issues actually appear in the sciences as well. And I think it's more important to try to address those questions and hopefully come to some consensus eventually. But once the consensus is reached, the questions often goes away from philosophy and becomes incorporated in the specific sciences. So in that way, philosophy contributes to science in an indirect way. So I think that is how one should think about philosophy. Specifically in philosophy of science, we like to question and discuss science and putting that into context and analyzing and critically evaluate different things that are taken for granted in these in the sciences. There are some philosophy of science that deals with kind of very general, broad issues in philosophy of science, and other that deals with more specific questions within individual sciences, such as physics or biology. And then we're dealing with philosophy of physics or philosophy of biology. And here we're, of course, talking about philosophy of physics. And there are two main types of questions. I'm not saying that these exhaust all the kind of questions we can do in philosophy of science, but still, one important thing is questions of interpretations. What does the theories mean? How should we understand their description of reality, and what do they tell us about that? And how should we understand the concepts and those kind of questions? Another thing is more questions that deal with scientific method. So these are kind of, in this description, two broad general types of questions that I would like to discuss more. So another thing I would like to say, that it's important to do philosophy of science well. It is important to have a reasonably good understanding of the specific sciences that you're dealing with and the questions. Otherwise it can go wrong in one way or another. And what we think that philosophers can do compared to the scientist or the physicist in this case is to come with more of an outside picture and a big picture, and question things that the physicist might take for granted, focusing on underlying principles and concepts and all that. And the philosophers bring kind of a different skill set to that. It's not supposed to be that the philosophers kind of tell us, the physicists, what they're supposed to do. That is not all what we're kind of interested in here. It's more like engaging in a constructive discussion. And ideally, we want to have scientifically informed philosophers discussing with philosophically informed scientists in a good way to help to develop science in as good way as we can. Now, I will just briefly talk about questions of interpretation. I will first talk about this in a very rather general fashion and talk about a question that is pretty central within philosophy of science. And that is, to what extent we should trust our theories as giving a correct description of reality. Remember that we have modified our theories throughout time, and hopefully we think of these as getting us better and better pictures in some sense. But what does that really mean? And many people do think that these pictures we get from the development of new theories gets closer and closer to describing a real reality. And if you think of that, and if you think that successful theories give us a good picture, and sometimes you're more of a scientific realist. Other people, who are called scientific anti-realist, only think of the theories as tools of making predictions and don't really think that we should think or dwell upon the question what this really tells us about some kind of underlying reality. So these are kind of the two more kind of extreme positions here. And of course it should be mentioned that when it comes to this issue, both among philosophers and physicists, there has been very different views. And interestingly enough, when I talk to some physicists, I've noticed that some physicists are much more realist and some others are much more anti-realist. And these are just among the physicists themselves. And of course within philosophy we also have this kind of debate where there are different views advocated. And furthermore, there are different intermediate positions that have been developed. Maybe we should trust the theory to some extent, but not fully. And what is the part we should trust and what shouldn't we trust, and these kind of things. This is not something I can go deeper into here, but you should keep that in mind. It might also be the point that I would also like to make the point that you might not have the same attitude to all different theories. Some theories you might look at in one way and some other theories in another way. Another issue that is quite interesting and perhaps the most debated question about interpretation within philosophy of physics is how to understand quantum physics and quantum mechanics. And there are many different views, and this has to a large extent been pushed by philosophers, even though some physicists have also looked into this quite a lot. Early on, in the development of quantum physics, the leading scientists were engaged in philosophical debates on how to understand the theories. And very classic is the debate between Bohr and Einstein. And interestingly, for a very long time, Bohr's views were commonly accepted by most physicists, and many physicists stopped thinking about this further. And it was to a larger extent philosophers that continued to think about the question of interpreting quantum physics in a way that many physicists didn't do. And there has actually been a shift now, and I would say that the dominance of Bohr's view, even among the physicists, is now much smaller than it once was. And other alternatives, other approaches to understanding quantum mechanics is now taken more seriously. That is not to say that you accept Einstein's views in all respects, because the alternatives we're discussing here are much more numerous than that. So. But there are a large number of different interpretations of quantum physics. And now I've just mentioned these interpretations of quantum physics, and they can be very strange. So like one example is the many worlds or Everettian understanding of quantum mechanics that postulate that there are all these different kind of parallel worlds popping out in one way or another. And all of this might sound pretty crazy. But these kind of things can be serious. The discussion and debates about these can be made serious. But I would like to warn you that there is also so much nonsense out there about quantum physics that you should perhaps be careful about. And one warning sign is that when many of the less serious people, they tend to take weird sounding and cool sounding things from all these different approaches and present them without actually giving any coherent picture and actually taking ideas from competing and contradicting approaches. And this often is just some kind of very fussy pseudoscientific nonsense can be generated in this way. So I warn you about that. So I've now talked about philosophy of science, and specifically philosophy of physics. I've addressed some general issues in philosophy of science and also talked about the interpretation of quantum mechanics and quantum physics, which is kind of one of the more central issues in philosophy of physics. But now I would like to address the question, why is philosophy of physics especially important for quantum gravity? One reason is actually that there is no finished theory of quantum gravity. And some people might think that is a reason for philosophers to stay back and just let the physicists do their job and wait until they have a well-established theory. But I think that is the wrong view. It's actually when the theory is in its kind of developmental stage as it is now, and where there is a lot of conceptual issues, that the philosophical reasoning and discussion about the theory might actually help to develop the theory. We don't think that the philosophers will solve that in themselves independently of the physicists. But I think if you have a constructive dialogue between philosophers and physics, the philosophy can actually contribute to the development of a better theory of quantum gravity. Another thing that is certainly philosophical is to discuss the question of scientific method and the rather controversial debate on various approaches to quantum gravity and their lack of empirical support. How should we think about that? Should we stress the importance to continue searching for experiment, or could we in some situations trust the theory even in the absence of new empirical results? And how could such a view be motivated? This is another thing that has been debated and discussed among philosophers, and is something that physicists themselves also discuss, and it's important to have a constructive debate about scientific method when it comes to this. Another interesting kind of little side remark that I think is useful, since I've talked about the interpretation of quantum physics, is that it might be the case that solving the problem of quantum gravity might be connected with, in some way or another, to solving the problem of understanding quantum mechanics. And perhaps they're connected in some way. Or perhaps they are not that connected and can be solved independently. We don't know yet, but it's an important question to keep in mind. And it's important to note that philosophy is probably most important when we have to change our view in a big way, when we have to reconsider the way we understand the world, and not just work within the theories, but actually kind of modify them. And then the philosophical questions are more important, and I think the questions with quantum gravity and dealing with that is certainly of that type. So this is basically just an introduction, and there will be other talks where we look more at specific questions and specific issues about quantum gravity from the point of view of philosophy of physics. Like, just mentioning one thing, many different approaches to quantum gravity suggest that at a more fundamental level, space and time are not really there. They are somehow emergent and appear in some rather intricate way from a non-spatiotemporal underlying theory. That might be the case, but we don't really know exactly how that would come about. But there are many conceptual questions here to figure out. Could such a thing be possible? And this is just one thing that we'll discuss in other talks. And I hope you will look at these other talks and that you appreciated this talk. And I thank you very much for listening to this talk.